Alright, thanks for joining me for tutorial 11. In the last tutorial we introduced simple linear regression and we talked about how to use linear regression to model the linear relationship between a single quantitative explanatory variable and a single quantitative outcome variable. So we're using the explanatory variable to explain or predict the outcome variable. This week we're going to continue this discussion by talking about simple linear regression assumptions, the coefficient of determination, and centering variables. We'll also introduce multiple linear regression, discuss differences between types and goals of models, and go over generalized linear models. A helpful way to remember the assumptions of simple linear regression is to use the mnemonic line. The first assumption is linearity. So the association between the two variables is linear, or the mean of y given x is a straight linear function. The second is independence. So the errors are independent, which is equivalent to assuming that the residuals are independent. The third is normality. So for each value of x along the regression line, the values of y are normally distributed. This means that the errors are normally distributed. And finally, the equal variance or Homoscedasticity assumption, which means the error variance is constant. In other words, the variation around the regression line is approximately the same at each point along the line. So now we'll go over how to check the assumptions for simple linear regression. We use a diagnostic or residual plot to check the linearity and equal variance assumptions. Independence is checked through knowledge of study design, and normality is checked using a QQ plot. So we check linearity using a residuals versus fitted plot. You don't have to know much about these plots other than that if there is no pattern to the residuals plotted against the fitted values, the linearity assumption is met. So if you do this in R, you're looking for no pattern to the residuals versus fitted and a smooth red line through the plot. We can also check for homoscedasticity using a residuals versus fitted plot. You essentially want the cloud of points to be fairly constant, and when they aren't, this is known as heteroscedasticity. The top plot on the left shows the most common way that heteroscedasticity will look, with a cone shape increasing to the right surrounding the line, whereas the plot on the bottom left appears to be fairly constant or homoscedastic, as the variation of the y values around the regression line is approximately the same everywhere along the line. The plot on the right also seems to be approximately homoscedastic. On the high and low ends of the line, the points are a little closer to the line than the middle, but for the most part this looks pretty good, and I would say that it approximately meets the homoscedasticity assumption. Remember that in the real world, our assumptions are rarely perfectly met, so we just want to see that these are approximately met. We check for normality using what's known as a QQ plot. If the line is a straight diagonal line, then this assumption is approximately met. Plots on the side show how QQ plots will look if the data are or are not normally distributed. The data on the top is normally distributed, so we can see that this appears as a straight diagonal line in the QQ plot. But the bottom two are not normally distributed. The middle plot is skewed to the right, and the bottom plot is skewed to the left. So a curved line appears in the QQ plots because the normality assumption is violated. And the QQ plot on the right looks fairly normal. So we talked a little bit about the R squared when we looked at the output in the last tutorial, but just to quickly review, the coefficient of determination, or R squared, tells us the proportion of variability in y that is explained by x. Its values range from 0 to 1, and the closer it is to 1, the better our model is at making predictions. If the R squared is 0.20, the interpretation would be that 20% of the variation in the outcome can be explained by the explanatory variable or variables if you have more than one explanatory variable, as we will with multiple linear regression. So just some final thoughts on simple linear regression before we move to some example problems. The first is that you should never extrapolate past your model. This is when you use a model to make predictions using values outside of your study range. So if your explanatory variable is age, and your sample only includes people aged 20 to 30, you should not try to make predictions for people aged 40. Also, outliers can have a really big impact on a model. There's a lot of debate about how outliers should be handled, for example, whether or not outliers should be removed from a data set. And we won't get into the details of that for this course, but what you should know is how removing an outlier would influence values like the slope, p-value, etc., like we discussed in the last tutorial. A final thing is that if your data fail to meet the assumption of linearity, so there's a non-linear relationship between x and y, one option is to transform the x or y variable. For example, you could do a log or square root transformation of the x variable. This might help to make your data meet the assumptions for linear regression, but the problem is that when you transform variables, the results are often difficult to interpret. If you log an x variable and the slope is 2, the interpretation is that for every 1 unit increase in logged x, there's a predicted increase of 2 units in y. So the interpretation is not exactly straightforward or all that meaningful. So let's try an example problem. A study was conducted to investigate the relationship between a diet pill and the development of colorectal cancer. Researchers selected 130 patients with colorectal cancer and found that 16 of them were on the diet pill sometime in their lives, while for 412 healthy controls that were selected, 14 of them were on the diet pill. Conduct a hypothesis test and calculate a measure of association for this relationship. So we can see that the explanatory variable, being on the diet pill, yes or no, is categorical, and the outcome, development of colorectal cancer, yes or no, is categorical. So the ideal hypothesis test, assuming the data meets the assumptions, is a chi-square test. The null hypothesis is that the diet pill and colorectal cancer are independent. The alternative hypothesis is that the diet pill and colorectal cancer are dependent. We know from the study description that the data were obtained from a random sample, and each individual only appears in one cell of the table. If we make a 2x2 table of our observed data, we would find that all of our cell counts are at least 1, and that the expected cell counts, calculated by multiplying the row total by the column total and dividing by the overall total, are at least 5. But we could also probably assume that these last two assumptions are met, given that we have a large sample size here. So we proceed with our chi-squared test and find that this gives us a chi-square statistic of 13.35 with an associated p-value of 0.0002. Since our p-value is less than our alpha of 0.05, we reject the null hypothesis and conclude that we have evidence to believe that the diet pill is associated with colorectal cancer. The next step was to calculate a measure of association for the relationship. If we go back to the study description, we can see that participants were selected on the basis of disease status. They selected controls to compare with patients with colorectal cancer. This means it's a case control study. So therefore, the appropriate measure of association is an odds ratio, because we can't estimate the relative risk with case control studies, as we've discussed in previous tutorials. Looking at the output, we see that the odds ratio is 3.99. This means that the odds of having colorectal cancer among people who took the diet pill is 3.99 times the odds of having colorectal cancer among people who have not taken the diet pill. Note that you could also calculate this odds ratio by hand based on the data in the 2x2 table. Let's try another example. A scatter plot of length and weight for 20 low birth weight infants is shown below. If the outlier from the plot below was removed, how would the slope change, intercept change, and residual standard error change? Remember that the residual standard error tells us how far individual observations move from the regression line on average. So the slope would increase because the outlier that was artificially decreasing the slope is removed. The intercept would decrease because the line is becoming steeper, which pulls down the left side of the line. The residual standard error would also decrease because on average, the predicted values are closer to the observed values, because we've removed the outlier, an observation that was far away from the regression line. In other words, the average distance between the regression line and individual observations is smaller now. Here's another problem. Researchers wanted to know whether test scores are different among females and males. Students were randomly and independently sampled. Conduct a hypothesis test using an alpha of 0.05. So here we have a qualitative explanatory variable with two independent groups compared, females and males. We also have a quantitative outcome, test scores. So the ideal test, assuming that the assumptions are met, is a two-sample t-test. The null hypothesis is that the median difference in test scores between females and males equals 0. In other words, the median test scores of males and females are the same. The alternative hypothesis is that the median difference in test scores for males and females does not equal 0. So here we're referring to the median and not the mean because, as you'll see, our assumptions for the t-test are not met. If we check our study design, we know that the sample was independently and randomly obtained, and that the groups are independent, men versus women. But if we look at the distribution of observations in the groups, we see that these are not normally distributed. So, because we don't meet the assumptions for a two-sample t-test, we conduct the non-parametric alternative, a Wilcoxon rank sum test. So we conduct our Wilcoxon rank sum test in R, which gives us a W statistic with an associated p-value of 1. So since our p-value is greater than 0.05, we fail to reject the null hypothesis and conclude that we do not have enough evidence to believe that there really is a significant difference in the medians of grades between females and males. So last week we talked a bit about how the intercept often does not have a useful interpretation. Using the example of gestational age as our x variable and head circumference as our y variable, the interpretation of the intercept refers to the mean head circumference with an age of 0. So this has no practical interpretation. So whenever the explanatory variable does not take on values close to 0, the intercept is not very informative to interpret. To make the intercept easier to interpret, we can center the x variable around its mean. So centering means that we subtract the mean x value from each individual x value. So if our explanatory variable is age, we subtract the mean age from each individual's age. When you center a variable, the shape of the distribution will not change. Only the location and scale of the x-axis changes. The scatter plot shown on the bottom left shows an example of an uncentered x variable, gestational age, with an outcome variable of head circumference. The scatter plot on your right shows the same plot with a centered x variable. As you can see, the scatter plot looks exactly the same, except that the scale of x has changed. For the uncentered variable, the mean on the x-axis is 200 days, and x values range from about 160 to 240. For the centered variable, the original mean of 200 is now 0. On this plot with centered age, the value of 20 refers to an observation that is 20 days above the mean age of 200 days, and minus 20 refers to an observation that is 20 days below the mean age of 200. We can also fit a model to the data using the centered age value. Above the plots are each of the regression formulas with uncentered and centered x's. As you can see, the slope associated with gestational age, 0.1099, is the same for both the centered and uncentered x's. But the intercept of 27.45 for the centered variable now has a more meaningful interpretation. This is the mean head circumference for a baby with the mean gestational age of 200 days. Whereas with the uncentered gestational age variable, the intercept of 5.06 was the mean head circumference for a baby with a gestational age of 0. So now let's talk about multiple linear regression. We use multiple linear regression when we have 2 or more x variables and 1 continuous y variable. The x's can be either continuous or categorical. With simple linear regression, we fit a line to examine the association between an x and y variable. With multiple linear regression, we are fitting a plane between a 3D cloud of points on what is essentially a 3-way scatter plot. The majority of studies are comparative and use observational data, where the exposure groups differ. For example, we could look at the effect of smoking on lung capacity, but the smoking and non-smoking groups might differ by characteristics other than smoking, like age. These variables may act as confounders, distorting our estimate of the association between smoking and lung capacity. But we can control for variables like age to estimate the association between smoking and lung capacity. So we can include age as an explanatory variable in a multiple linear regression model, along with smoking, to control for it. And this will tell us the relationship between smoking and lung capacity, adjusting for or controlling for age. So let's say we're interested in fitting a model with 2 explanatory variables, where one of these variables is categorical and the other is numeric. For example, let's say we want to look at the effect of gestational age on head circumference for mothers who smoked and mothers who did not smoke. This is essentially like we are fitting 2 regression lines, one for smokers and non-smokers. But rather than fitting 2 separate equations, we fit one model, which gives us 2 separate regression lines for the 2 groups. So there are 4 different things that can happen when we model this. Let's say that smokers are red and non-smokers are blue. On your top left is a model where smokers and non-smokers have the same intercept and same slope. This model is saying that smoking is not important. The lines are pretty much exactly the same. On the top right is a model where the 2 lines have the same slope, but different intercepts. This model implies that smoking is associated with a reduction in head circumference, but the rate at which head circumference increases with gestational age is the same for those who smoke and don't smoke. On the bottom left is a model where the 2 lines have different slopes and different intercepts. This model implies that there is an effect modification, or that the variables gestational age and smoking interact. The rate at which head circumference increases with gestational age is different for smokers and non-smokers. The effect of gestational age is modified by smoking. And it can also be stated that the effect of maternal smoking is modified by gestational age, or in statistical terms, that the variables gestational age and smoking interact with one another. On the bottom right is a model where the 2 regression lines have the same intercept, but different slopes. And this is a special case, which we aren't going to cover in this course. So the goals of a regression model can be broadly placed into one of 3 categories. The first is descriptive. So here we are simply attempting to describe relationships that may exist. We're not interested in making any sort of predictions. We're only interested in examining the direction of associations that may exist. With predictive models, our goal is to build a model that is good at making predictions for the outcome. We still must have a good reason to include the explanatory variables that we include, but the ultimate goal is to build a model that is good at predicting the outcome variable. With comparative models, we want to compare 2 or more groups, populations, or treatments, but we include other variables in our model to control for confounding. For example, we could compare an exposed and unexposed group, like smokers and non-smokers, on lung capacity, and include other variables, like age, to control for confounding. And as mentioned, the majority of health studies are comparative. The specific type of regression model we use depends on the type of outcome variable that we have, whether this is numeric, categorical, a rate, or a survival time, or others. The multiple linear regression models we've discussed so far only apply when the outcome variable of interest is numeric, and the explanatory variables may be any mix of numeric and categorical variables. These models can be extended or generalized to incorporate outcome variables that are binary, a rate, or survival time. Logistic regression is used when the outcome variable of interest is categorical and binary. For example, does one have the disease? Yes versus no. Poisson regression is used when the outcome variable of interest is a count or rate at which events occur. So for example, the rate at which people contract a disease. Often, Poisson regression is used when working with aggregated data. Cox regression, which is also known as survival analysis, is used when the outcome variable of interest is time until an event occurs. For example, how long does a patient survive after diagnosis of disease? For each and all of these types of regression models, the explanatory variables may be any mix of numeric and categorical variables. For those of you taking SPPH 500, we'll expand on these types of models in that course. So let's try an example. Suppose you wanted to develop a model for predicting weekly sales in thousands of dollars for individual stores based on number of customers who made purchases. A random and independent sample of 20 stores were selected. You want to know what the predicted weekly sales are given that 900 customers made purchases. So the outcome that we're predicting, weekly sales, is continuous, and our explanatory variable, number of customers, is also continuous. And we want to use the number of customers to predict weekly sales. So we would want to fit a simple linear regression model. But first we have to check the assumptions. We know that the Y values are independent from the study design, as stores were randomly and independently selected. But we also want to check for linearity, homoscedasticity or constant variance, and normality. With simple linear regression, you can check each of these three assumptions with a scatter plot, like the one shown on the top left, but you can't check these assumptions with a scatter plot with multiple linear regression. So we want to use better methods to check these assumptions. So we can check linearity with a residuals versus fitted plot. So we can see that there's no pattern to the residuals plotted against the fitted values, and there's a straight red line through the plot. So this assumption is met. We can also check the homoscedasticity assumption with the residuals versus fitted plot. We can see that the variation around the regression line appears to be fairly constant. And finally, we can check for normality with a QQ plot. And we can see that this approximates a straight diagonal line. So all of our assumptions for simple linear regression are approximately met. So we estimate a simple linear regression model in R and find that our intercept equals 3.162 and our slope is approximately 0.008. So we put this information in the regression equation, multiplying the slope of 0.008 by 900 customers and adding the intercept of 3.16. And this gives us 10.36. Our outcome is in thousands of dollars, so this tells us that given that 900 customers made purchases, one would predict that weekly sales would be $10.362 thousand. Note here that it's always important to know your study units and use these to report your findings accurately. If you had just reported this as the mean weekly sales as 10.36, then readers might think that this means dollars rather than thousands of dollars. So it's important to always be clear about the units of your variables. A few other things that you might be interested in are the p-value associated with the slope and the r-squared. The p-value tells us the probability of obtaining the slope we did, or one more extreme, merely by chance, assuming that the null hypothesis is true, that the slope equals 0. Since it's less than the alpha of 0.05, we reject the null hypothesis that the slope for the association between customers and sales equals 0, and conclude that we have evidence to believe that the slope is not equal to 0. The r-squared tells us the proportion of the variability in sales that can be explained by customers. In this case, the r-squared of 0.9136 tells us that 91.36% of the variability in sales can be explained by customers. Here's another example. To evaluate the effectiveness of two different smoking cessation programs, smokers are randomized to receive either program A or program B. Of 6 smokers on program A, 1 stopped smoking and 5 did not. Of 6 smokers on program B, 4 stopped smoking and 2 did not. Which statistical test would you use? So the explanatory variable is the program, either A or B, and the outcome is quitting smoking, yes versus no. So, assuming our assumptions are met, we would use a chi-squared test. So the first thing we do is make a 2x2 table of what we observed. Of 6 smokers on program A, 1 stopped smoking and 5 did not. Of 6 smokers on program B, 4 stopped smoking and 2 did not. We can then check our assumptions. We know from the study design that this is a simple random sample and that each individual appears in only one cell of the table. So we have independent observations. We can also see that all observed cell counts are at least 1. And our last assumption is that all expected cell counts must be at least 5. We calculate the expected counts by multiplying the row total by the column total and dividing by the overall total from our observed table. If we do this, we can see that the expected cell counts are lower than 5 in all of the 4 cells. So, since our assumptions aren't met, we should use Fisher's exact test, the non-parametric alternative to the chi-squared test. Here's another example. To the right is a histogram that shows the distribution of the length of stay for all hospital discharges in California. If a random sample of 1,000 discharges were taken from the California All Discharge database and a histogram were made of patient length of stay for the sample, what would the histogram look like? So we're taking a sample of individual discharges from the larger population and plotting these as a histogram. So we would expect that the histogram would appear to be exponential, the same shape as the population distribution of patient stay length. And we would expect the sample mean to be similar to the population mean. We would not expect the histogram to be normally distributed because we are not looking at the distribution of the sample means. So the central limit theorem does not apply here, even though we have a large sample size. If we were to instead take numerous samples of 1,000 discharges and calculate a mean for each of those samples, and then we plotted those means, this is where the central limit theorem would apply, and this is what we would expect to look normally distributed. Here's another example. 200 hypertensive patients are randomized to either a diet program or exercise program. Blood pressure is measured on each patient twice, before the program start and 3 months after the start of each program. What statistical procedure should you use to determine whether or not the change in mean blood pressure was statistically significantly different between the 2 programs? So our X variable is binary categorical, diet program or exercise program, and our outcome is continuous, blood pressure. An important thing to note here is that we're looking at repeated measurements, before and after, for each of these groups. But the research question is asking about how we would determine if there was a statistically significant difference between the 2 programs, not before and after for one of these groups. So independent groups are being compared here. So ideally, we would want to do a 2-sample t-test here if our assumptions are met. So we would do this by comparing the change in scores for each of the 2 programs. So we would subtract the after blood pressure value from the before value for each person in the diet program and do the same for those in the exercise program. And we would then compare the mean change in scores for the 2 groups with a 2-sample t-test. The next question is, what statistical procedure should you use to determine whether or not there is a difference in mean blood pressure before and after the program among patients in the diet program? So now the research question is asking about before and after for the diet program only. So in this case, it's asking about paired data from those in the diet program. So we would use the paired t-test here. Here's another example. Measurements on a random and independent sample of babies born to mothers who took drug A during pregnancy were compared to measurements of babies born to mothers who did not take drug A. A statistically significant difference in the mean head circumference was found between children born to the two groups of mothers. So based only on this information, which of the following can you conclude? So let's go through all of the potential answers. First, there's a 3% chance the alternative hypothesis is true. So the p-value is not the chance that the alternative hypothesis is true. It's the probability of observing the difference in mean head circumference between children born to the two groups of mothers, or more extreme, merely by chance, assuming the null hypothesis is true, that there really is no difference in the mean head circumference for the children born to the two groups of mothers. The next one was taking drug A during pregnancy causes a reduction in child's head circumference. So first, we can never say causes based on a statistical test using observational data, only that you have evidence to support the alternative hypothesis. Also, based on the information provided, we don't know whether drug A is associated with higher or lower head circumference, only that there's a statistically significant difference in head circumference for children from the two groups. C is taking drug A is associated with an increased child's head circumference. Again, we cannot infer this from the information provided. We only know that there's a statistically significant difference in head circumference for children from the two groups. But we don't know if drug A is associated with higher or lower head circumference based on this p-value alone. And D, the sample mean difference in children's head circumference between children born to the two groups of mothers is clinically important. So this isn't correct either, because we only know that there's a statistically significant difference between the two groups. But we don't know if this difference is clinically or practically important. This could be a small difference that really isn't all that meaningful. So our answer is E. None of the above can be concluded from the information provided. In the next tutorial, we're going to do a course review and go over some practice questions to help you prepare for the final exam.